Good day and greetings to our lecturer. We are Group 16, and this presentation is about our linear algebra group project. In this project, we solve a system of linear equation using analytical and numerical method. Hi, my name is Muhammad Afif Zaim bin Muhammad. My matrix number is S24A0479. For the introduction, linear algebra is widely used in many fields, such as engineering, science, and computing. In this project, we focus on solving a system of linear equation written in matrix from Sx equal B. We generate a unique 3 by 3 system using a seed value based on our group student ID. The system is solved analytically using Gaussian elimination and verified using Python. We also apply the Jacobi iterative method to observe its behavior. This project helps us understand the importance of difference solution method and the connection between mathematical theory and computation.
Hello everyone, my name is Ahmad Razin Arifuddin and I will be presenting part 1 of our project, which focus on data generation. Before we could solve any equation, we need to establish a unique and fair dataset. To do this, we use Python to generate a 3 times 3 matrix A and vector B based on a specific seed value. To make the data specific to our group, we derive this sheet from our student identification numbers. As you can see on the screen, we collected the metric numbers of all 7 group members and extracted the last 4 digits from each. For example, my ID ends in 0472 and my teammate digits range from 0466 to 0487. Once we had this digit, we calculated the total seed value, represented by S, by summing all 7 set of digits 0479, 0474, 0472, 0487, 0471, 0468, and 04x3. We arrive at a final seed value of 3334. We then plug this value into the NumPy random seed function in Python to log in our data generation process. You might wonder why we use this method. The main reason is reproducibility. By using a fixed seed value tied to our IDs, we ensure that the same metric and vector can be regenerated consistently every time the code is run. The guarantees that our data is unique to our group while remaining mathematically verifiable and fair for all members. This stable dataset allows us to move forward with our analytical and numerical solution with confidence.
Assalamualaikum and hello everyone. I am Mujahid and I will presenting part one which will focus of our Python implementation for data generation. To ensure our project is unique and fair, we didn't just pick a random numbers. Instead, we created a reproducible seed value derived from our group's identity. We took the last 4 digits of every member's student and ID and summed them up. This gives us a total C value of 3334. By using this specific number as our starting in Python, we ensure that our data is specific to our group but can regenerate exactly by the same way by anyone else. Based on our seed of 3334, the Python code generated the following system as a matrix A is as you can see, matrix A, and a vector B is These integers serve as coefficients for the system of linear equation that my teammates will solve in the next section. Turn this seed into a mathematical system. We utilize the NumPy library in Google Colab. NumPy is essential here for three reasons. First, reproducibility. We use the NumPy random seed function to freeze the randomness. This means every time we run the code, it produces the same result as well. Second, efficiency. NumPy handles metrics as a native objects, allowing us to generate our 3 times 3 matrix A and 3 times 1 vector B with just a single line of code using the reading function. Third, verification. It provides the linear algebra submodule which we use to calculate the determinant and later verify our manual Gaussian elimination result. Finally, we had to interpret this result to ensure the system was actually solvable. We use Python, NumPy, linear algebra determinant A function which calculate a determinant of minus 799. Mathematically, a square matrix is only invertible if its determinant is not zero. Since the answer is minus 799 is definitely not zero, we confirm that matrix A is invertible. This is a crucial green light for our project because it proves that a unique solution exists for X, making it suitable for both our analytical Gaussian elimination and our numerical Jacobi testing. Now, I will pass the floor to the next presenter to explain the manual solution.
Assalamualaikum warahmatullahi wabarakatuh. My name is Zulfakri Haikal bin Muhammad Zulkiman. My metric number is S24A04X7. So I will be presenting for part 1, which is matrix properties. To begin our project, we needed to generate a unique and reproducible dataset. We use a seed value derived from the last 4 digits of the student ID numbers of all 7 group members to ensure fairness and transparency. As shown in the slide, by summing these IDs, we calculate a total seed value of 3334. This seed was then used to initialize the random number generator in Python using the NumPy library. This process produced of uh, our 3 times 3 matrix A, which you can see on the screen. The first row starts with value -9, 8, and -5. This systematic approach ensures that our data is specific to our group while remaining consistent for repeat computation. Once we obtained matrix A, our next step was to analyze its technical properties. Starting with the determinant is a scalar value that provides critical information about the matrix behavior. We calculate the determinant manually using the 3 times 3 formula by breaking the matrix into smaller 2 times 2 matrix. As shown in the calculation steps, we multiply -9 by its corresponding minor. We subtract the product of 8 and its minor. Finally, we add the product of -5 and its minor. After simplifying the arithmetic, we found the determinant of matrix A is -799. We also verified this result using Python's function, which confirmed our manual working was 100% accurate. Finally, we look at what this determinant value tell us about our system of equations. In linear algebra, a square matrix is considered invertible if and only if its determinant is not equal to zero. Since our calculate determinant is -799, which is clearly not to zero, we can formally conclude that the matrix A is invertible. This is a crucial finding for our project for two reasons. First, it guarantees that the system AX equal to B has a unique solution. Second, it confirms that the system is stable and suitable for the analytical methods like Gaussian elimination that we will perform in the next session. This concludes the validation of our data. We now have a solid mathematical foundation to proceed with solving the system. I will now hand the presentation over to the next speaker.
Assalamualaikum warahmatullahi wabarakatuh. Hi, my name is Ahmad Arif. In this part of our project, we focus on solving a system of linear equation using Gaussian elimination. This method is one of the most systematic approaches in linear algebra to find exact solutions. The system set up analytical solution using Gaussian elimination. The system we are working with is derived from the metric equation Ax equal to b. It consists of three equations with three unknowns, x1, x2, and x3. The equation, you can see the uh, picture we give. This represent is a typical linear system where our goal is to find the value of x1, x2, and x3. For our augmented matrix, to make the system easier to solve, we represent it in augmented matrix form. The augmented matrix combines the coefficient and constant into one structure. So we combine the uh, matrix AX equal to B to be augmented matrix lah. This format allows us to apply row operations step by step. Okay, so the next is introduction to Gaussian elimination. Gaussian elimination works by transforming the augmented matrix into an upper triangular form. The process involves three main steps. First, we select a pivot element. Second, we use row operation to eliminate variables below the pivot. Finally, once the matrix is triangular, we apply back substitution to solve for each variable. This method is systematic, reliable, and widely used in solving small to medium-sized systems. And transition to next part. In the following steps, we will demonstrate how Gaussian elimination is applied to our system and how the solution is verified using Python. This ensures both mathematical accuracy and computational confirmation. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Harif Rani bin Abdul Bari. My matrix number is S24A0468. I will present about system setup and Gaussian elimination. Okay, moving on to part 2. Based on the problem statement, we construct this system of linear equation. To solve this analytically, our first step was to convert the system into an augmented matrix. As you can see, the coefficients are on the left and the constant are on the right. Our main goal here to apply Gaussian elimination to find the exact value for S1, S2, and S3. Next, we apply elementary row operation. First, we normalize the first row to make the pivot equal to 1. Then we perform elimination step to remove S1, S2 from the lower row. After completing the step, we successfully reduce the matrix into an upper triangular form. As you can see here, we now have 0 below the main diagonal, which make the system solvable. Okay, when we have the upper triangular matrix, we use back substitution. We start from the bottom row to find S3 first, which give us approximately negative 0.5081. Then we substitute this value back up into row 2 to find x2, and finally into row 1 to find x1. So the final analytical solution vector for our system is shown here. X1 is approx 0.59, S2 is negative 0.15, and S3 is negative 0.50. Okay, to verify our manual calculation, we use Python. We run this code to function on the same matrix. As you can see in the output, the Python result match our manual calculation perfectly. We also compute a time x, and it's return the original vector, which is negative 4, negative 4, and negative 2. This mathematically confirm that our analytical solution is correct. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Amir Zakwan bin Norman Hisham and my matrix number is S24A0474. For the part 3, in this section, we attempted to solve a system of linear equation using the Jacobi iterative method. As you can see here, we rearrange our three equations so that x1 is defined by the first equation, s2 by the second, and so on. To start the process, we feed the computer an initial guess of all zero. Next, we go to Python implementation. The most important line to notice is where we copy x to x all. This is the definition of the Jacobi method. We use the values from the previous step to calculate the new step simultaneously. We set this to run for 5 iterations to see how the values behave. Okay, this is where it gets interesting. Instead of the number setting down to a specific answer, they explode. In just 5 steps, we went from single digit to number in the thousand. This behavior is called division. The method is failing to find a solution. So, why did it explode? The Jacobi method isn't magic. It's required to metric to be diagonally dominant. This means the number on the diagonally needs to be bigger than the sum of the number in that row. When we check our rows, we see that 9 is smaller than 13 and 1 is smaller than 8. Because this condition isn't met, the math guarantees that the answer will diverge. In conclusion, this experiment proved that we can just throw any equation into a computer solver because our system lacked diagonal dominance. The Jacobi method failed. For a system like this, we will need to rearrange the equation or use a different method entirely.
In conclusion, this project demonstrated how a system of linear equation can be solved using both analytical and numerical approach. We successfully generated a reproducible system using a seed value based on our student ID and solve it analytically using Gaussian elimination. The solution was then verified using Python, confirming its accuracy. When the Jacobi iterative method was applied, the result showed this divergence, highlighting the importance of matrix properties such as diagonal dominance. Overall, this project helped us understand the strong relationship between mathematical theory and computational tools in linear algebra. Thank you.